Hello everyone. Today we're going to do our first problem with Coulomb friction. The system that we're going to study consists of a mass on an inclined plane. It's attached to a spring that has a stiffness constant of 15,000 newtons per meter. The mass is equal to 10 kilogram, and there is a harmonic force pulling on the block with an amplitude of 90 newtons at a frequency of 25 hertz. Since there is contact friction, we also have a coefficient of dynamic friction equal to 0.3. We're asked to calculate the steady state amplitude and the equivalent damping ratio when A, the theta is equal to 0 degrees, and B, when theta is equal to 30 degrees. Now the first thing we're going to do here is to try to find an expression for the normal force right here, because we know that the friction force is proportional to the coefficient of dynamic friction or static friction, depending on the case, multiplied by the normal force. So the way that we're going to do that is by doing a force balance in the y direction. It's pretty simple. We have the normal force acting upwards minus the weight. That's equal to 0. We're at equilibrium. And so we deduce that the normal force is equal to the weight, which is in turn equal to mass times the acceleration. Now, the expression for the steady state amplitude of a system where there is Coulomb friction is given by the following formula. You either find it in one of your textbooks or make your own cheat sheet. Here we're only concerned with solving the problems. In other videos, we're going to actually show where the formulas come from. So it's F naught divided by the stiffness constant multiplied by 1 minus 4 times mu times the normal force divided by pi times F naught. We square this. All of this is divided by the absolute value of 1 minus r squared, where r is equal to the excitation divided by the natural frequency. And so we have, for F naught, we said that was equal to 90 divided by 15,000 multiplied by 4 times 0.3 times 10 times 9.81 pi times 90 all right, divided by the absolute value of 1 minus the excitation frequency. We're given the excitation frequency is equal to 2 times pi times the frequency, which is times 25 hertz, divided by the stiffness, 15,000, divided by 10. That's the expression for the natural frequency. And what we're going to find is that the steady state amplitude is equal to 0.0003531 meters. That's the first part of our answer. After that, the expression for the equivalent damping ratio, let's write it over here, it's the damping coefficient, the equivalent damping coefficient divided by 2 times the mass times the natural frequency, which when expressed in terms of coefficient of dynamic friction, steady state amplitude, is equal to 2 mu, the normal force, divided by pi times the steady state amplitude times the mass times the excitation frequency times the natural frequency. And so we're going to plug the values that we have. 2 times 0.3 times 10, 981, again because the normal force is equal to the mass times the acceleration, pi times the result that we had for the steady state amplitude, times 2 pi times 25. That's the excitation frequency, times the square root of 15,000 over 10. So we find that the equivalent damping ratio is equal to 0.8722. And we're going to highlight this as well. That's it for A. We're going to go to B now. I already did part of the work. I drew a free body diagram and I did a little bit of geometry just to show that the angle theta right here is the same as the inclination of the plane. So the angle between the normal force and the weight is equal to the angle of the plane. Our coordinate system, we aligned it with the block so that it makes our equation solving easier. Just as before, we're going to do a force balance in the y direction. So we have the normal force pointing upwards minus W, and here we're going to take the cosine of this triangle minus mg cosine theta equals 0. So the normal force is equal to mg cosine theta. Essentially, we're just going to use the same formula as before, but we're going to replace the normal force by, or rather, multiply the normal force by the cosine of the angle. So the steady state amplitude is given by, we said, F naught over K square root of 1 minus 4 mu n divided by pi times F naught. So we write this out. We have 90, that doesn't change, divided by 15,000. Now remember the normal force, we need to multiply it by the cosine of 30. All of this is divided by the absolute value of 1 minus, we said, 2 pi times 25 for the excitation frequency, divided by the square root of 15,000 over 10. All of this squared. So we get a steady state amplitude of 0.0000 0.3622 meters. We're going to highlight this guy. And just as before, we said that the equivalent damping ratio is equal to the equivalent damping constant over 2 times the mass times the natural frequency, which is equal to 2 times mu times the normal force over pi times the steady state amplitude, the mass, times the excitation frequency times the natural frequency. And what we get is 2 times 0.3 times 10 times the gravitational acceleration times the cosine of 30 . Two pi times 25 for the excitation frequency, and the natural frequency, which is again the square root of 15,000 over 10. So finally, we get 0.7364 unitless, and that concludes our problem. Again, if you want to have this worksheet as a PDF, I've put a link in the description below. Thanks for watching.